Okay, we're reviewing today for tomorrow's Unit 5B test. So we're going to run back over the notes real quick, and if we when we get done, we'll have time to ask some questions. Now, it's been a long time since we've had a new unit test, so there's a lot of lessons that we have to go back through, a lot of information. But do not expect necessarily that a lot of the skills that we went over between coming back from Christmas time and now, a lot of those skills may not show up necessarily on the test. For example, we worked on how to multiply and divide polynomials. It's unlikely that you will face a question that will simply say, hey, here's two polynomials, multiply them, or here's two polynomials, divide by synthetic division. Okay, it's probably not going to be like that, but what you may have to deal with is that a problem may require you to multiply two polynomials in order to work out something that they've got going on in a problem. Okay, so a lot of this stuff was kind of building up to basically 2 or 3 lessons. But so ultimately we've got like 10 or 11 lessons that were just kind of the prerequisites, the needed skills that were there so we could do the last 2 or 3 lessons. Okay, so let's take a look. We started way back in the beginning looking at polynomials. Okay, this was really very simplistic. Okay, we just talked about a polynomial. A polynomial, the word itself simply means a series of terms that are being added or subtracted. Okay, and we saw that we had specific names. Okay, monomial was the name that specifically meant a polynomial that had only one term. Binomial was a polynomial that had only 2 terms. Trinomial was a polynomial that had only 3 terms. And then as we exceeded 3 terms, we simply called things polynomial from that point on. Okay, we also picked up a definition for degree or order. Okay, the degree or order of a polynomial is simply a representative value that tells us what's the highest exponent that goes along with that polynomial. Okay, I believe the rest of that was examples. Okay, and the next day we started looking at some math. Okay, so multiplying polynomials. Come on, computer, keep up. Okay, we very quickly saw that multiplying polynomials was very heavily involved in the distributive property. Okay, we've all seen from back in the day multiplying binomials, like what was at the bottom of the screen right here, where a lot of you were trained to use the FOIL method from back in junior high. Okay, but we dismissed the idea of FOIL method simply because there are larger polynomials that are out there, and if all you do is multiply the first terms, outer terms, inner terms, and last terms. Okay, as you can see in this instance, there's a couple of terms that get missed along the way, and the bigger the polynomial gets, the more terms will get missed. Okay, so we simply said instead of FOIL or any other cute catch name or anything like that, we just simply say when it comes down to multiplying polynomials, you need to multiply everything from the left polynomial times everything from the right polynomial. And an easy way to remember how many terms to expect was to count the terms in the polynomials. Like in the one on the screen that you have there at the bottom, there's 2 terms in the binomial out front, there's 3 terms in the trinomial at the back. Okay, 2 terms times 3 terms would be 6 terms. You would expect 6 terms to come out from this multiplication, and that'll work no matter how big the problems get. I believe the rest of this was all examples, and you can look back at those if you are in need of some extra problems to look at. Okay, we spent a couple of days after that looking at long division. I'm not sure if you will need division really of any sort, but since we were going through all of the math of polynomials, we definitely did these. And once again, you're not going to have problems come out and say you need to use long division here or you need to use synthetic division there. It'll be up to you to decide which method might be good for a particular problem. This file is enormous. Okay, so the computer's really struggling with it. Trying to get to the ones where it actually has some real larger polynomials in them. Again, these problems are all worked out in your notes for you. If I can find it. Okay, problems like this. Okay, where we have a binomial or a polynomial being divided by another polynomial. Uh-oh. There we go. Come on. All right, there it is. Okay, the 2 main things that you have to remember with long division with polynomials is however many terms you have in your divisor. Okay, the divisor is the guy that is doing the dividing. He lives outside of the little house structure, the x plus 1 in this case. Okay, however many terms he has in him, that's how many terms of space it will require in order to divide into the polynomial. So in this case, here you got the x plus 1 as your divisor. He has 2 terms in him. It's going to take 2 terms worth of space to be able to divide in. So the first value that you will be able to write above our house little division structure there is above the 9x. Okay. Also, remember that whatever values you invent coming across the top of the division, it's like a distributive property there. Okay, it has to multiply times both of these terms, and you get, in this case, 2 results because there was 2 terms in the divisor. Okay. Looking at one kind of being worked out. Remember, we invent a value up top. It comes out. It distributes. We get 2 terms worth of an answer because there was 2 terms in the divisor. Okay, and with the long division, once you get your stacks going like that, then you subtract. Okay, you subtract your values coming down the stacks, and then you drop your next value. Go back up to the top of the problem, invent your next value. Okay, and again, remember we're subtracting as we come down the stack, so we're trying to get this left-hand value, left-hand term right there, we're trying to get them to match up. So when we subtract, they eliminate themselves. Sometimes we end up with no remainder as we have right here. Okay, but it's always possible that we will end up with a remainder. Okay, and remember how the remainder is structured over here on the very right side of the screen. Okay, whatever the remainder is goes over whatever your divisor is. So in this case, 0 over x plus 1. That's where the remainder would belong. Okay, so look back at that if you need a refresher on how the long division method works. Okay, and synthetic division. Once again, just a procedure. Get my computer to catch up here. Again, these files are quite large, so the computer's struggling. Okay, synthetic division, a little bit easier for a lot of folks simply because we'd already spent a little time banging away at the long division. It's the same idea, same repetitive procedure to it, just a little bit of a different structure. Keep in mind, as you have at the top of the screen there, you may only use synthetic division when your divisor is the structure x plus or minus some kind of a constant. Okay, so you can't use it if it's 2x's or negative 3x's or half an x. It's got to be 1x. Okay, and can't be x squared, x cubed, or anything like that. It's got to be x to the first. Okay, so here's the structure down at the bottom of the screen. We take our coefficients from our problem, and something I did not mention in the long division, make sure you don't skip any terms. Okay, if the problem wants to start off with x to the 10th or something like that, that's fine. 10 has been established as the degree or the order. That means that x to the 9th has to be represented, x to the 8th, x to the 7th, x to the 6th, and so on. It may not skip any terms coming down the line. Okay. When we set up our structure, all we need for synthetic division is the coefficients, like you see down at the bottom of the screen. Okay. And the only real catch is when we put a number out here in the box, this is our divisor, we are going to reverse his sign from the problem. The problem said to divide by x plus 1, so we put in the box x minus 1. And the reason why we change the sign, okay, is because when we come down our stacks here in a moment, we're not going to subtract like we did with long division. We're going to add them up. Okay, so synthetic division, the first term always drops straight down. Okay, and then after something drops down underneath the line, you multiply times the box, and you write it down in the next space underneath your coefficients from your problem. So in this case, 2 times negative 1 is negative 2, and when we get our stacks, we add. Okay, it's different. How come it doesn't subtract like it did with long division? We've already done the sign change. Okay, long division, we had to change the sign as we went. Sign change is already done, so we can just add them up rather than subtracting. Again, anytime anything drops down below the line, you multiply it times the box, and when you get a stack, you add them up. Okay, the thing that caused people the most trouble on this is to remember that the last number, the right-hand term that drops down, that is your remainder. That's your numerator of your remainder. Okay, so he goes over the divisor. The next term over coming back to the left, that's your constant. The next term coming back would be your x to the first, and the next one would be x squared, the next one would be x cubed, and so on. Okay, so look back at this file if you have some difficulty with synthetic division. Okay, after that, we switched gears a little bit and started looking at basic factoring skills, and this is something that we we still need to get kind of programmed in the back of our head. The very first problem, or the very first thing that you look at when you are instructed to factor for any single problem, no matter how many terms it has, is things in common. Okay, we're going to look at all the terms, in this case a 6x squared and an 8x, and we're going to ask ourselves, okay, the 6x squared and the 8x, do they have something in common? Do they have a coefficient in common that we can take away from them? Do they have variables in common that we can take away from them? Absolutely, that needs to be done first, whether it's a binomial, trinomial, whether it's going to be completing the square or the A times C method, any of that. Okay, basic factoring is the first skill. Okay, the rest of this was just examples. Okay. Now we started to look at the A times C method. Okay. When it comes down to factoring trinomials, there's special rules in place for going along with stuff, and one of the things that we watch for, particularly with trinomials, is if we can find, okay, these two steps going on in the problem at once, then we can factor the trinomial by this method. Okay, we're going to look at the A term and the C term, and of course we're talking about A x squared plus bx plus c, okay, those being your A and your C. Whatever those are, those two values, if you take A times C, you're going to get a product of some kind. Okay, some number. We're going to take that number, we're going to break it down into factor pairs, meaning it's going to break down into two numbers that multiply together to equal that number. Okay, looking at those factor pairs, we want to be able to find a factor pair that will add or subtract to exactly equal the B term, including its sign. Okay, if we can find that situation, okay, as this one shows, okay, if we can find that situation where we can add or subtract two of our factors to equal the B term, in this case the 2 and the 4, okay, then we may take that information directly to the answer. And again, this is only when the A term equals 1. If the factors of the 8 that work out are the 2 and the 4, and they're both positive, then that's fine. Your solutions are x plus 2 and x plus 4. Okay, and as always, you may always multiply those binomials back together to see if you get your problem back as a way of checking it. Okay, so that's the A times C method. Okay, and that was when A is equal to 1. But what happens if A is not equal to 1? Okay, well, it doesn't change the strategy or anything. Okay, we are still looking for the situation where we're trying to find a pair of factors, okay, from the result of A times C. So in this case, A times C was a negative 12. Okay, we are searching for factors that could add or subtract, in this case, to equal positive 1. Well, a negative 3 and a positive 4 would get that done. Okay, however, we may not just jump straight to the answer, okay, if the A term is not a 1. So what we do is we build what we call the box. Okay, on the left-hand diagonals, typically where I put this information, I put the ax squared and the c term straight out of the problem. Just put them on a diagonal together. Okay, and the other two boxes on the other diagonal, these are going to be our new b terms based upon the factors that you discovered. Okay, so negative 3 and positive 4, those are both x terms. Okay, so we put them in there together. Okay, now the goal or the purpose of this is because we are going to factor in the box. We're going to look at what the rows have in common with each other. We're going to look at what the columns have in common with each other. And those two commonalities are going to give us our factors. Okay, so in this case, we ended up off the rows with an x and a 2. On the columns, we ended up with a 2x and a negative 3. Those are the terms for our answer. 2x minus 3 and x plus 2. Okay, and again, you can check this method just like before. Okay. Now we kind of sidestepped from the thinking part of factoring. Okay, we weren't necessarily trying to find this A times C and figure out how it adds and subtracts to equal B. This was more, okay, straight, cut, and dried. When the problems fit certain formats, we may factor them based upon some provided formulas. Okay, and there's 3 formulas that we looked at. One of them is the difference of 2 squares, and then there are sums and differences of 2 squares. Okay, so just going to kind of very quickly look. Okay, when you look at a problem, if it's a binomial, Okay, we can look at the two terms in the binomial and we can decide, will the two terms both break down to be perfect squares? Okay, and by perfect squares we mean that you get exactly one term times exactly the same term to equal that first term. And if you take the second one, if it will break down to exactly some value to multiply times the exact same value. Okay, it's like a square root. Square root of 25. It's a perfect square because it is exactly 5 times 5. Breaks down to the exact same value twice. Okay, so if that happens and it is a subtraction problem between them in that binomial, then you may factor. Okay, whatever the square root of the first term was, we plug it in for A, and whatever the square root of the B term is, we plug it in for B. And it's really that simple. You plug in your values and it is factored. Okay. We said we cannot factor the sum of two squares. Okay, so it does not matter if x squared breaks down perfectly and y squared breaks down perfectly. If it is an addition sign in between them, it will not be factored. So remember that. Okay. There is one for a sum of two cubes, and this works very much the same way. It's just a formula to plug into. All we have to do is look at the problem and decide, hey, we've got a binomial. They're being added together. Can I take these two terms and break them down? Take that first term and break it down into something times something times something where it's the exact same thing all three times. Okay, and the trail term, can I take it down and break it into something times the same thing times the same thing? That would be perfect cubes. Okay, so whatever you decide how it breaks down, the A and the B, you simply plug them in, A and B, all the way through the formula. And you do usually have to do a little bit of simplifying after you plug in to the formula there. Okay. And lastly, the difference of two cubes works identically to the sum of two cubes. The only difference is, of course, it is being subtracted rather than added. Okay, and these formulas, I went back in. If you need to be your mind's refreshed how to build the formulas and all that kind of stuff, then be sure to look back at the notes from this day, listen to the videos. I tell you how to construct those formulas. Okay, the rest of this was examples. Okay, completing the square. This is where a lot of people got sideways on some things. Okay, completing the square is something that we were struggling with. Some of us are still struggling with it because we never did it to begin with, and then we never did anything to figure it out. Okay, but completing the square is kind of a last gasp option. Okay, if you cannot get the A times C idea to work, then you may have no other choice except to adjust the problem into a different format so that it may factor better for us. Okay, so you do your A times C, check and see if it works. If it does, great. If it doesn't, fine. What we're going to do is we're going to take that problem and we're going to say, okay, problem, you're not working out. We're going to fix you so that you will. Okay, so what we're going to do is we are going to adjust the constant of the trinomial. To do that, we send the old constant to the other side of the problem, kind of like that. And then we need to invent a new C term. Okay, now inventing the new C term. Okay, this is what's causing some people so much trouble, and it's for a silly reason that's causing us trouble. You're going to take the b coefficient, the number in front of x, and we're going to take half of it. Sometimes that's going to give a whole number. Sometimes that's going to give a fraction. Okay, if it gives a fraction, so what? It's just a number. Okay, it is absolutely just a number. I'm not sure at what point in time somebody guaranteed you that everything in math was going to be whole numbers, and if it wasn't a whole number, you just give up. Okay, but it's going to be fractions sometimes. We're going to take half of it and we're going to square it. Whatever the result of that is, we add it into both sides of the equation, because whatever we add into one side, we have to add into the other to keep the equation balanced. Okay, so there is the idea. Okay, now this guy on the left-hand side that you're looking at down there, he factors. Okay, and I'm not going to go back into the generic example because it is very difficult to follow. We'll go back and we'll look at the one that has some numbers in it. Okay, so here's the problem we started with at the beginning. Okay, if we decide that completing the square is the deal, we move the C term to the other side of the problem, and we invent a new C term by taking B, which is 2 in this case, we half it, knocks it down to 1, and then we square it. So in this case, our new C term is a 1. We take that 1 and we add it into both sides of the problem. The reason we do this is because we have just invented a perfect square trinomial, which means it will break down into some value times the exact same value. Okay. Turns out that the value is a binomial. Okay, and the thing you need to remember is how to get to this from this trinomial in the second step to this binomial squared in the third step is that the lead term, okay, the x right there, is the result of taking the square root of x squared. Let's see if my computer will keep up and let me write on the page or not. Okay, maybe not. But you take the square root, there we go, square root of the lead term, and that will give you a result as your lead term. Okay, I'm hurting my computer's head here. I think I'll stop writing on the screen. Okay, and the trail term, you get the exact same thing. You take the square root of the 1 from the trinomial. That gives you your trail term. And the only thing we get from the b term in the trinomial is the sign. Since it was plus 2x, we keep the plus. If it had been minus, then this would be a subtraction binomial there. And the only thing left that you have to do is bring the constant back over to the right side of the problem, and you've got your answer. It's factored. Okay, so look back at that if you need help. Okay, and forms of quadratic equations. Okay, this is where we looked at the difference between standard form, which is what we are familiar with from back in the day, and vertex form, which is actually what we were discovering how to get to by the completing the square method. Okay, something to remember there. Okay, we've got the introduction of h and k into our formulas. Okay, h and k is the vertex of the parabola. Okay, also keep in mind that the formula has a built-in subtraction sign in between the x and the h. Okay. Let's see. I believe the rest of this was just converting back and forth, okay, which is just a skill. You may need to practice that. And lastly, a lot of information on the parabolas. Okay, so we know what the parent function looked like. We introduced the vertex form, so we kind of already seen that. We introduced the possibility that our parabolas could open sideways if they wanted to by reversing the variables, basically taking the inverse. Okay. Also remember, and this is something I did not point out or emphasize very strongly in some classes, and that's my fault. Okay, if you are going to inverse, okay, the variables, like in this case the x and the y, have been reversed. That's also going to inverse the x and the y from the center point. Okay, so h and k will flip-flop as well. K represents information about the y value for the vertex, so he definitely needs to be connected to y. H represents information about the x value of the vertex, so he needs to affect x. Okay, so if x and y are reversed, then h and k are reversed as well. Okay, so we took a quick glance back at the inverse with the reflection. Okay, and several pieces of information that I imagine we're probably going to have to spend a little bit of time studying. Got to get them in our heads here. Okay, the parabola is going to open in the direction of the first dimensional variable. You're just going to have to memorize that. The sign of x squared, when everything's all said and done, that sign will tell us particularly which direction, okay, whether it's going vertically up or vertically down or vertically or horizontally left or horizontally right. That comes from the sign of A. Okay, as A's coefficient gets smaller and smaller and smaller, that's going to widen the parabola. It's making it slower going to infinity. And as A gets bigger and bigger, that's going to make it skinnier because it's in a bigger hurry to go to infinity. Vertex is at h comma k, no matter which direction it is going, okay, whether it is a vertical parabola or a horizontal parabola, the vertex is always at h comma k. So don't get that idea of h and k reversing. Okay, for a horizontal parabola, don't get that. Don't let that think that it reverses in the vertex also. That's not true. Parabola has a line of symmetry that passes through the vertex going the same direction as the parabola, and that was pretty much it. The rest of this was just examples. So there's a lot of information in there. Okay, so there's a basic summary of what you're needing to know in order to have a shot at being successful on your test.